Addition and subtraction. Adding and subtracting rational expression, radicals and roots. The way that we can add and subtract radicals is if the index and what is inside the radical are the same. And if they are, we can just go on and add the coefficients. So if we look at this first one here, we have the 4th root of 10 plus 7 times the 4th root of 10. So both of these here, we have the 4th root of 10. The radicals index and what's inside of it are the same, yes? So what do I have? 1 here and 7 here. So we have as long as the radicals, the root and what's inside are the exact same, we can just add them together. Now, if we look at the next one, we have 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. Well, here, because we have 2 8 to the 1/5, and we have 10 more, so what do we have? We got 12 of them. No, because really 8 to the 1/5 is the same thing as saying the 5th root of 8 and the 5th root of 8. It's just written in a different form. It's written in our exponential form instead of in our radical form. Well, that's it. That's all we have to do for this here. Because 8 to the 1/5 will not simplify, because 8 is 2 cubed, but we can't take the 5th root of 2 cubed and get a whole number. So we get this here. Any questions on any of these so far? Okay. Let's look at the next one. I'm going to erase that so I have a little bit more room. We have the cubed root of 54 minus the cubed root of 2. Are those the same? No. So we need to look at the 54, because 2 is as simplified as it gets. We can't take the cubed root of 2 because 2 is prime. But let's look at 54 and see if we can simplify this at all. So, factor tree. What number do we know, or what set of factors for 54? 2 and 27. There are other factors, but I do know for sure 2 is going to work, because if we're going to be able to add or subtract them, 2 has to be a factor. Well, 27 is what? 9 and 3, and 9 is 3 and 3. So we can factor this all the way down. So really, when we look at the cubed root of 54, it's the same as the cubed root of 3 times 2. Cubed root of 3 times 2. And we rewrite it this way because, again, we can take the cubed root of 3 cubed. The cubed root of 3 cubed is 3. Cubed root of 2 minus cubed root of 2. So we can have this here. Now are the radicals the same? Well, yes. So now I have 3 of 1 and I'm taking 1 away. So how many do we have left? So 2 cubed roots of 2. 2 times the cubed root of 2. And that's it. That's all we have to do for this here. Any other questions on this here? Any questions on anything we've done so far? All right. Look at the next page. 7 times the 5th root of 12 minus the 5th root of 12. So here are the radicals the same. Okay, so let's go on and subtract. 7 minus 1 is? The 5th root of 12. And that's it. Because they are the same, we can go on and add or subtract. How about problem number 11? What did we get? 9 to the 2/3. And that's it there. I mean, we could simplify 9 to the 2/3 a little bit, but we'll leave it as this here. So any questions on any of this here so far? Okay, well, let's look at the last one here. Because we have the cube root of 5 plus, okay, we're going to have to rewrite cube root of 40 because they're not the same. We can't just add or subtract them together. So we'll need to factor 40. 5 times 8. 8 is 2 times 4, and 4 is 2 times 2. So we get these nice factors here. We'll know we'll have 5 inside, but since I have 3 2's, we know we can pull that out front. Yes? Because the cubed root of 2 to the 3rd is just 2. Because we had 3 2's, we can pull them out. Any questions on this here? Well, the last thing we need to do is add these together. Cubed root of 5 plus 2 times the cubed root of 5 is 3 times cubed root of 5. And that's it. Questions on this here? Okay. Properties of rational exponents and radicals can be da 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 da. Now, a variable, just a variable x, can be positive, negative, or 0. We can plug any value we want in for a variable, yes? So, let me get another page. I'm going to explain and kind of go into detail about this with, let's just use examples to try to see how this works. Okay? So, say we have the square root of x squared. What is the square root of x squared? X, okay? Now, let's let x equal negative 2. So, on the left-hand side, if we take the square root of negative 2 squared, let me write that a little better. Negative 2 squared is what we have, yes? On the left side, we're saying it is what? Negative 2, right? Because the square root of x squared is just x. So if I say x is negative 2, it should equal negative 2, yes? So let's work this out. What is negative 2 squared? It's positive 4, yes? Because a negative times a negative is a positive, yes? And the square root of 4 is positive 2. These are not equal, are they? No. And this is what this is getting into. Is the order of what things matter. So if we take an even root of a variable, we have to add absolute values. Not always, but we need to. And really, the kind of emphasis here is if it's not to an even power. We have to add the absolute value bars. Because if it is to an even power, well, any time so we multiply a number by itself an even number of times, it's still going to be positive. Because anything to an even power is positive. Anything squared is positive. Fourth root is positive. So if we end up having something like x squared, no matter what number I put into it, it will always be positive. But if it's just left as x, like we just saw, we have to take care of that case where it could turn out to be negative. So if it comes out, if we take an even root, then what's left over is an odd power, then we've got to put the absolute value bars. So we're going to start simplifying some of these expressions with variables. So we're looking at this one first, the cube root of 64 and y to the 6th. Well, we can break this up, cube root of 64 times cube root of y to the 6th. Well, what would be the cube root of 64? Right, it's 4, because 4 to the 3rd is 64. So we can simplify that as 4. This cube root of 64 is 4. And it works out nicely. The calculator will do this for us. Now, the variable, what we can essentially do is divide it by the root. We can divide whatever the exponent is by the root, or we can subtract it out. Well, why can we divide it by the root? Well, remember, we can rewrite radicals as rational exponents. The exponent, so the 6 goes on top, and the root is on bottom. Well, 6 divided by 3 is 2. And we're done with this here. Now, because it is an odd root, we took a cubed root, an odd root, we don't have to worry about absolute value bars. We don't have to worry about positive or negative. We're fine with odd roots. So any questions on this here so far? Any questions on anything we've done so far? Okay. Let's look at letter B, this division. With any of these here, it might be a little bit easier to look at this split up. Because again, when we talk about these roots here, we can split them up with the numerator and denominator. So we can split them apart. So the fourth root of x to the 4th divided by y to the 8th, we can split it apart to the fourth root of x to the 4th divided by the fourth root of y to the 8th. We can split them into 2 parts. Now I'm going to do exactly what we did on the previous one, is we can rewrite these as fractional exponents. Since x is to the 4th power, it's going to 4 on top, and since the root is 4, 4 would go on bottom as well. Now for the denominator, we would have y. The exponent would be 8, and it would be over 4. Now these work out nicely to do them this way, because, well, 4 divided by 4 is 1. 8 divided by 4 is 2. We have nice whole numbers, yes? So it's nice to do this way, this way, because we can see that we get these whole number answers. We'll have x to the 1st on top and y to the 2nd on bottom. So it works out nicely here. We'll come across some where they don't reduce all the way, and we'll see a different way we can look at it. What else do we need? We need absolute value bars around the x, because here we took an even root. So we have to take care of the fact that these cannot be negative. These answers cannot be negative. Now, y squared is fine, because any negative that is squared times itself will be positive. So that will take care of itself. But since the x is to an odd root, we have to add the absolute value bars. We have to add the absolute value bars. Questions on either one of these here? I will tell you on the homework assignment, if one of these comes up, it's going to have you add the absolute value bars. It's going to mark it wrong otherwise. All right. Let's look at the next one. The cubed root of 27d to the 12th. All right, let's look at the cubed roots. Can we take the cubed root of 27? It is 3. I'll just go on and write that. 3. Because we can type that into the calculator, the cubed root of 27. If there's a number, we can try it in the calculator and see if it will give us an answer. And it gave us 3. Now the variable, I'm going to rewrite it as our fractional exponent. So the numerator is going to be the exponent inside, which is 12. And the root is our index, which is 3. We have 3. D. 12 divided by 3 is 4. 3d to the 4th. And we leave it as this here. There's no need for absolute value bars because we took an odd root. We took the cubed root. So any questions on this here before we move on to the next one? All right. So we have this here, the 4th root of x to the 4th over y to the 16th. So if we want to, we can rewrite this using our fourths as x to the 4th, or the 4th root of x to the 4th over the 4th root of y to the 16th. We can rewrite it as this here. We can also do our fractional, our rational exponents. So for x, 4 on the inside would go on top. The root would go on bottom. The same thing with y. The 16 would go on top, and the 4 would go on bottom. So what would we get if we simplified this? X over y to the 4th. And we're completely done, yes? We need absolute value bars around the x. It's not always going to be just the numerator. It's just worked out on these last few. The numerator has an odd exponent. It's to the first power, so it's odd. If it had been x over y to the 3rd, we would have needed absolute values around the whole thing. It's just worked out the denominator has an even root, or an even exponent. Now, could it work out that we don't need any exponents at all? Well, yes. Because if it had worked out to be x squared over y to the 4th, we don't need anything because x squared has an even exponent, y to the 4th has an even exponent. So we don't need the absolute values. Now, even if it had been x to the 3rd, we still need absolute values. It's any odd root they're going to do this on. Questions on this here? Now, with most mathematics, they're going to do that, have you enforce the absolute values, and then they're going to throw it out the window. Because here, assume all variables are positive. Well, since the variables are all going to be positive, we don't need the absolute value bars anymore. So if it includes this, we don't need the absolute value bars anymore. If they don't include that in the instructions, you're going to need the absolute value bars. Okay. Might need a little more space. So when we look at this here, we're taking the 5th root. Now, the mathematical approach to this here would be really rewriting each one of these out as a rational exponent. Writing each one out as a rational exponent. That would be the mathematical way to do this. So you don't have to write this down, and I'm going to write this on the whiteboard. this is what they're going to want. This is how mathematically, if you pull up the textbook, this is how they're going to show it. They're going to show this step and then simplifying down. But we know with taking radicals, anytime we have a group of 5 over 5 for these fractions, we can remove 1. 1 will come out.
Dylan Davis, please come to the office. Dylan Davis, please come to the office.
One of them will come out. One of them will simplify out. So when we look at this here, we can do that in a less mathematically written way. And I just look at each one. I look at each one of these terms. Can we take the 5th root of 4? Is there a number of times itself? 5 times. That'll give us 4. Well, no. 2 times 2 is 4, and that's about it. Okay? It's not going anywhere. I put it on the inside because I know I can't take the 5th root of 4. So I'm just moving from one term to the next. Now, a to the 8th. Well, I can do 5th roots of this because I have more than 5 of them, because each time I have 5, we can move 1 out, yes? So, the one way we can kind of think about it is we start at 8. Well, I can remove 5 of them from it, yes? I can do that once, because 8 minus 5 is 3, yes? Can I do it again? Well, no, not. I could, but I'd get a negative number, right? So how many times did I subtract 5? So how many come out? 1. So 1a comes out. But how many do I have left over? 3, yes? So what stays inside? A to the 3rd. Okay? Four A is done. So we're looking at 14. B to the 14. Well, I can pull 5 out at once. 14 minus 5 is 9. Well, 9 minus 5 is 4. Can I do it again? No. How many can I pull out? So here would be B squared. We got those 3 taken care of. Questions on this here? Last one, C to the 5th. Well, yes. We can take 5 out, which would give us 0. I can pull 1 C out. Oh, I forgot to write B to the 4th. That's it. We've taken care of everything. Questions on this here? Because if we looked at this with our rational exponents, well, 4 to the 1/5 doesn't change. Here we would have A to the 1 3/5, B to the 2 4/5, and C to the 1. A would move out, B squared would move out, C. Leave us with the 4th root of 4A cubed B to the 4th. It's the same type method that we're doing. It's just a little bit reduced, not as rigorous as some would say. Form of doing this. Questions on this here? Okay, so we're going to skip. We're going to do this one here, then we're going to go back. We're going to skip back and forth because I realized after I printed these sheets off that I want these paired together. So we can see another example of this. Okay. Cube root. So let's go one term at a time. Can we take the cubed root of 2? No, so it stays inside. Okay, done with 2. A to the 13th. Well, we can. So if we wanted to do this on a calculator, we can do 13 minus 3, which would be 10. So there's 1. We can just keep going. 10 minus 3 is 7. 7 minus 3 is 4. 4 minus 3 is 1. I can't go any further. So how many times did we do it? 4 times. So how many come out? 4. So over here we would have b to the 4th. Not b to the 4th, a to the 4th. A to the 4th. Now how many do we have left over? 1. So we would just have a. All right, that took care of a. Now we're moving on to b. That would be 3 minus 3, which is 0. So we just have b. Done. And lastly, we have c to the 8th. And we can do the subtraction of 3. 8 minus 3 is 5. 5 minus 3 is 2. We can't do it anymore. So we're able to do this twice. And that left us with 2. Questions on this here? Any questions on anything we've done thus far? We're good with this here? Awesome. So that is your answer. All right, now we're going to back up. Write each expression in simplest form, assume all variables are positive. Now this here, what we're doing here is similar to what we did the other day with our numbers. When we talk about changing, because we had the 5th root of 8 in the denominator, where we changed it to 2 to the 3rd and then simplified it out that way. We're doing the same thing here. So we have x, well, be good if I can write. We have x over the cubed root of y to the 8th. Now, as we can see here, we can simplify this a little bit already, yes? Because 8 is bigger than 3. It will reduce down. But we still need to get it so that this radical reduces completely. Because for this to reduce completely, that exponent with y here has to be divisible by 3 for this to reduce all the way. So what is the next number after 8 that is divisible by 3? 9 would be the next one, yes? How many am I missing to get to 9? 1, because if I had another y, it would make it y to the 9th, and that would reduce. So what we can do is I can multiply the numerator and denominator by the cubed root of y. Now the numerator is going to be a little bit easier to work with because it's x times the cubed root of y, which is x times the cubed root of y. They just multiply together. The x stays outside because it's not inside a cubed root. They would have to be inside a cubed root for it to multiply together. Now the denominator, y times y to the 8th, would give us y to the 9th, but it would be in the cubed root. X cubed root of y. So what is the cubed root of y to the 9th? What would that be? It would be y to the 3rd. Now another way that we can look at this here is really saying that we have y to the 9 thirds, because the fractional exponent in 9 divided by 3 is 3. And that there would be our answer. And since we don't have any extra variables on top and bottom, nothing that can simplify out, this is our answer. So any questions on this here? Are we good with this here? Yes? They wouldn't, because the y on top is to the 1/3, essentially that cubed root. It's stuck in there, so we can't do anything with it, with the denominator. It'd be very tempting, but because it's just the cubed root, we can't. Now, if it had been xy times the cubed root of y, then those y's would cancel. It would need to be outside the root. Okay. We're going to skip again back to this here, because I want to look at another one of these divisions before we look at the other type. So if we look at this again, this one here, well, it'd be nice for the radical to reduce. Now, since it is a cubed root for y to the 13th, we really need it to be y to a number that's divisible by 3. Because for this to simplify this here, really we're saying we have y to the 13 third. So if I want that to reduce, we need a number divisible by 3. Yes? Yeah, 15. 15 would be the next number after 13. That would be divisible by 3. Well, how many more y's do I need to get from 13 to 15? 2. So what we do is we multiply the numerator and denominator by the cubed root of y squared. Because this here will help us simplify the denominator to get the radical out of the denominator. On the denominator, we're going to have the cubed root of y to the 15th, because we have the 13th times y squared will give us y to the 15th. Now in the numerator, we're going to have x squared times the cubed root of y squared. And again, nothing in the numerator simplifies down any further than this here. Now, the denominator, if we wanted to, we can rewrite it as a rational exponent, which would be 15 over 3. And well, 15 divided by 3 is 5. So we have x squared times the cubed root of y squared all over y to the 5th. And that's it there. Any questions on any of this here? Okay. That's right, we're going to go back to C, this here. Okay. Write each expression in simplest form. Assume all variables are positive. So we have 14xy to the 1/3 over 2 times x to the 3/4 times z to the -6. Let's use our properties that we know. Well, we can simplify the numbers pretty easily first. What is 14 divided by 2? 7. So 14 divided by 2 is 7. That's not bad. So we've taken care of the numbers. Now we have x over x to the 3/4. Well, if the bases are the same and we're dividing, we subtract the exponents. So here we'd have x, well, the numerator is 1 minus 3/4, because the denominator will always go second. Well, next we have y to the 1/3 on top. Are there any y's on bottom? No, so we just have y to the 1/3. Now we only have z's on bottom, but we don't have any on top. But since it's to the -6, we need the exponent to be positive. And how can we make it positive? If we move it from the denominator to the numerator. Anytime we move it across a fraction bar from numerator to denominator or denominator to numerator, either direction, the sign of the exponent changes. So since it's z to the -6, if I move it to the numerator, It becomes z to the 6th. And I can move it back down and make it negative. Any one, moving it from the numerator to the denominator or denominator to the numerator, changes the sign. Well, I only have one last thing to do. 1 minus 3/4. It would be 1/4. And that's it. Okay, let's look at this here. Well, we can start off with the numbers first. We have 16 over 8, or 16 divided by 8. What is 16 divided by 8? 2. 16 divided by 8 would be 2. Now we have x next. Well, the numerator is to the first minus the denominator exponent, which would be 2/3. Because when the bases are the same and we're dividing, we subtract the exponents. So that takes care of x. So it leads us next to y. Well, y is just going to be to the 1/3 because there's not a y in the denominator, so we don't need to do anything with it. Now lastly, z to the -4th on bottom. Well, since the exponent is negative, we can move it from the bottom of the fraction to the top, which takes it from being to the -4 to just the 4th power. And the only thing really to simplify is our x term. 1 minus 2/3, we can make the denominators be the same, or we can plug this into a calculator. 1 minus 2/3 is going to be 1/3. Then we'll have y to the 1/3, z to the 4th. And we have this here. Any questions on any of this here so far? We're good with this here? Yes? Okay. This is the last thing we're going to look at. Perform each indicated operation, assume all variables are positive. Now, just like when we added or subtracted radicals with just numbers, the same thing is true with variables, or variables and numbers. Because as long as the radicals are the same, the root and what's inside, we can add and subtract. So looking at this first one here, the 5th root, 5 times the square root of y plus 6 times the square root of y. Well, both of them have the square root of y, yes? So we can do 5 plus 6, which is the square root of y. Questions on this here? Okay. So let's look at the next one, this one here. Are the radicals the same? Well, not quite. We do have the same root. We just don't have the same thing inside. Now, looking at both of these here, we're going to have to adjust both of them. Because if I look at the first one, the cubed root of 2z to the 5th, well, z to the 5th can reduce. Because when we have variables, the exponent inside can't be bigger than the root. Because if it is, that means it can reduce. Now, the other one, the cubed root of 54 is z squared. Well, z squared is fine. I can take the cubed root of 54, or I can simplify the cubed root of 54. let's look at 2z to the 5th. Well, looking at this here, I'm not able to take the cubed root of 2. Well, the other one doesn't have a 2, but 2 is already too simplified. We can't take the cubed root of 2. Now, the cubed root of z to the 5th. How many times can I pull 3 z's out? 1. And how many do I have left over? Because we're only able to subtract 3 once. We're only able to pull a group of 3 out once. And once we pulled that out, we had 2 left over. Okay. So this is as simplified as it gets, so we can pull it back in here. So we'd have 12z times the cubed root of 2z squared. So I didn't include the 12 when we were simplifying it, but we do have to put it back in place. Any questions on this here so far? Okay. Well, we've gotten that taken care of. Now we need to look at the other one. We need to look at the cubed root of 54z squared. All right, guys, we'll pick this up tomorrow. We're not going to have time to finish this.